Anxious eyes search the little face on the pillow, looking for a sign that might bring hope. Anxious eyes. Of what avail are they at times like these? Of what avail? Let's see. Let's go down the corridor a little way. Here, too, are anxious eyes, but eyes fortified with a microscope. Through it, through lenses smaller than the head of a pin, science looks for that sign of hope. As it observes and analyzes the struggle against disease, holds the answer. An airplane zooms over a cloud-covered ocean. The horizon is concealed, yet the plane stays on its course. For inside the cockpit, inside this bubble sextant, is another horizon, a man-made horizon, a tiny, ever-visible bubble of air between lenses, enabling the pilot accurately to compute his position. Where lies the way? Optical science holds the answer. Even in airplane construction, optical science performs miracles. For example, raw materials, are they up to standard? A sample from a large batch of metal is selected at random. Either an electric arc or spark is used to vaporize the specimen. And then, in this amazing optical achievement, the spectrograph, the light from the vaporized metal is made to pass through a system of lenses and prisms that break it up into its own particular spectrum or pattern of light waves. When the pattern is photographed, translated into an arrangement of lines, the sample will not only have revealed the secret of its own composition, but also of the entire batch from which it came. For through the spectrograph, metal writes its own formula. By the groupings or position of lines like these, can be detected the presence of all known elements, down to 1/10,000,000th of a part. Here are aluminum, copper, chromium, and like every element in nature, they write their own signatures in their own individual arrangement of light waves. Raw materials, are they suitable? Optical science holds the answer. Throughout modern manufacturing, optical instruments play significant roles. The metallograph, for instance. While the spectrograph tells us the ingredients of any given sample, the metallograph shows the structural pattern within. By means of the metallograph, the structure of a material can be studied before it is put into use. Its pattern will reveal whether it is capable of withstanding future stress and strain. When industrial metals are found fit, the contour projector comes into play. To create interchangeable parts, the tools that form the metal have to be exactly right. Thanks to the contour projector, the dimensions of a new cutter, for instance, may be readily checked against original blueprint specifications as its magnified shadow image is thrown on a screen. Deviations to 1/10,000th of an inch can be detected. Interchangeable parts, the secret of mass production. Each unit must conform with every other unit, fit exactly into position. But will they? And will they function properly? Once more, optical science holds the answer. Today in industry, there is constant checking for accuracy. Various measuring instruments are used, and their accuracy is determined by other instruments, micrometers and master gauges. These super measuring devices are checked by what is known as an optical flat, a glass whose perfect surface reveals the slightest irregularity in other surfaces. With such precision and by such methods has man mastered the magic of metals. Crime detection. Bullets were fired by the same gun. The police microscope can convict a public enemy. Here, too, optical science holds the answer. Nothing escapes the lenses. Bullet markings are identical, and a photomicrograph provides permanent, incontrovertible evidence. Yes, optical science is every place. On the farm where destructive insects, plant and animal diseases must be observed and studied before they can be overcome. The dairyman keeps microscopic vigil over the milk we drink. In the petroleum industry, precision blending of high-octane gasoline by optical methods through use of the refractometer and other instruments. Optical science helps the paper industry analyze pulp, determine mixing qualities, and many other characteristics. It enables the food manufacturer constantly to meet food standards and specifications. Without optical science, there could be no motion pictures. There could not even be sound recording, for optics are the very heart of film recording equipment. Photography in all its forms depends on optical instruments or optical devices. So does the whole field of graphic arts, the pictures that go into our books, magazines, newspapers. Yes, whether it's a matter of giving more beauty or more knowledge to the world, or building a mightier bridge, or a taller skyscraper, or providing faster transportation, wherever we turn, we find that optical science is indispensable. Until America entered World War I, optical glass, so difficult to produce, was imported from Europe. Suddenly, the supply was cut off. The nation's war effort seemed jeopardized. In this emergency, one institution was ready, the Bausch & Lomb Optical Company. For since 1912, their ceramic engineers, under the direction of William Bausch, had been conducting experiments. The major obstacles had been overcome. Soon, optical glass was being produced here in volume that supplied 65% of America's 1917 war needs, and in quality, second to none in the world. Thus, through distinguished service to the nation, was a new scientific industry born, optical glass making, developed in the United States in 1917. And a new star was added to the firmament of American achievement. Since that date, Bausch & Lomb alone among optical instrument makers has produced all its own glass. Dozens of varieties especially designed for a multitude of purposes. Some for eyeglass lenses, some for use in highly complicated instruments, but all manufactured to the exacting standards of Bausch & Lomb's Scientific Bureau, where come the optical problems of many industries, many lines of research, problems demanding the coordinated skills of many specialists. And here, such coordination is found, for here, optical instrument making is completely controlled from raw material to the finished product. But no matter how elementary or how complex the optical requirements in any given situation, everything begins with the creation of the glass. First, any given formula must be translated into terms of raw ingredients. The exact proportion of fine white quartz sand, plus what other ingredients may be specified: potash, lime, antimony, arsenic, barium, boron, lead, zinc. Whatever chemicals are required for a particular kind of optical glass are blended together. They form a mixture, and the transformation starts. The mixture is ladled or charged into preheated clay pots already in the furnace and slowly melted. The tremendous heat has to be constantly and carefully controlled, just as the stirring of the mixture has to be controlled. Every mixture has its own chart, its recorded history minute by minute, degree by degree. Then, after being subjected for approximately 24 hours to a temperature of nearly 2,700 degrees Fahrenheit, the contents of the pot are ready to come out. Molten glass now. Pots containing glass for optical instruments have to be handled differently from others. Covered with insulated drums, such glass is put aside to be slowly cooled or annealed. Batches that are intended for eyeglasses, however, are poured while they are still white hot. And a moment later, a roller passes over the liquid mass, leaving in its wake a flat sheet of solid glass. This also must be slowly annealed. After cooling, large sheets are cut down to sections, each section subdivided into squares, each square about the size of an eyeglass lens. Reheated and pressed into molds, the squares become lens blanks. In special ovens, they're slowly cooled and then cemented to blocks, shaped to fit the curvatures of various types of lenses. Now, long hours of grinding by these tireless machines, fascinating to watch. And more hours of polishing. Further inspections and the factory operations are complete. An eyeglass lens emerges. A miracle in a quarter ounce of glass. Power to renew man's vision, to extend his useful life, to promote his happiness. Now let's go back to the glass intended for optical instruments. It's been cooling for many days, so the clay pot is broken away. A pot can be used only once for most types of instrument glass. Trained eyes detect the slightest imperfections. Skilled fingers remove those imperfections, for only flawless glass is usable. After rigid inspection, it follows one of several courses. Here it is being reheated, and after pressing becomes blanks for fashioning into lenses and prisms of scientific optical instruments. Where extreme curvatures are called for, blanks must be individuated on machines like these. Blank prisms are mounted on blocks, and the blocks are then prepared for prism grinding, a highly specialized process. After grinding, long hours of precision polishing. Here, as throughout, nothing short of perfection will do. To make sure of perfection, the optical flat is employed. The flawless surface of the optical flat is held against the surface to be tested. The pattern of reflected light rays between the two surfaces, Newton's rings they're called, reveals deviations from surface regularity as slight as 6/millionths of an inch, the smallest unit of measurement known. Ground and polished, just like its big brothers, even a tiny microscope lens, no larger than the head of a pin, has to pass the same exacting tests as large lenses and prisms. It, too, has to be perfect. It also is checked by optical means, those same Newton's rings, and when this minute masterpiece is declared satisfactory, it joins the rest of the family. Here are just a few members, finished products, ranging from the very small to this, a huge searchlight reflector mirror. Here are the optical elements that go into a microscope. And here in a sectional view is how they are arranged inside the microscope, one of the oldest and still the most universally used of all optical instruments. And here is the famous DDS research model, a marvel of optical and engineering skill, yet employing the same basic principles upon which all optical instruments depend. What are these principles that have given man his greater vision? One of them is the principle of refraction. Light rays traveling through the air comply with universal law when they encounter a denser medium such as glass. To illustrate the law of refraction, we draw a dotted line perpendicular to the surface of the glass. Now, when a light ray reaches the surface at this angle and enters the glass, it is bent toward the perpendicular, or as it is called, the normal. As it leaves the glass, it veers away from the normal. In the same manner, we can take a triangular section of glass or prism. When the light ray enters the glass, as before, it is bent toward the normal. And as it leaves, it veers away. This is the principle of refraction. Let's see how it works in actual practice. Here are parallel beams of light. Let's interpose a triangular prism in this manner. The light rays are refracted like this. By bringing two prisms together so that their bases meet, we cause the two paths of light to cross. The light rays are obedient to basic optical law, a law that never changes. Through the application of this law, as it relates to curved surfaces, we can bring light rays to a focus. This is the principle of the convex lens, and the purpose of that lens is to focus rays of light. On the other hand, light rays to spread, we can introduce a prism like this, and another prism like this, and the rays fan out. This is the principle of the concave lens. When light rays strike the concave lens, they spread. But when the angle at which light rays strike the glass is increased beyond a certain point, the rays no longer are refracted, they are reflected. Using this principle of reflection, optical science is actually able to bend light around corners. These are the principles, reflection and refraction, which has already been explained, that are the basis of so many wonderful optical instruments. This familiar prism binocular, for instance. Here are its lenses and prisms before assembly, each one a link in the optical chain that brings distant objects closer. In a sectional view, we can observe their complex arrangement inside the binocular, just one of the many instruments by means of which greater vision is made available to man. Greater vision through precision-made optical glass that harnesses and controls rays of light. Precision-made glass, born in fiery crucibles to be transformed into the eyes of science and industry. Eyes that helped create America's civilization. Eyes that safeguard that civilization in time of national emergency. For again in 1941, as in 1917, America found Bausch & Lomb ready to turn the accumulated skills and resources of peacetime to the grim necessities of war. Ready for our warships with searchlight mirrors, binoculars, rangefinders. Ready for our planes with aerial camera lenses, goggles, bubble sextants. Ready for our anti-aircraft units with height finders and flank spotting scopes. Ready for our big guns on land and sea with the fire control apparatus that gives them the deadliest accuracy in the world. And so, for outstanding accomplishment in war production, Bausch & Lomb was among the first group of 14 manufacturers to receive the famous Navy E pennant. It was the first concern in America to fly the Navy E Burgee with 1 star added, representative of continued accomplishment. And it was one of the relatively few that received not only the Army Navy E flag, but also a succession of added stars for constant adherence to difficult production requirements. These and other honors and tributes are testimonials of Bausch & Lomb's contribution toward American victory in World War II. More complicated than any optical device is the human eye. Our eyes are the most precious things we have, for through them, according to psychologists, we receive most of our mental impressions. Those impressions, whether sharp or distorted, clear or foggy, may determine success or failure, pleasant experiences or hardship. But before lenses can help bring greater vision, the trained specialist must make his diagnosis, determine each person's requirements. For seldom do 2 pairs of eyes see alike. Even a person's 2 individual eyes may see differently. To detect these differences and visual deficiencies, Bausch & Lomb designs and manufactures instruments for many types of examinations. And the professional examiner who uses them is especially skilled in their manipulation and in the interpretation of their findings. First, using the hand ophthalmoscope as an illuminator, he makes a preliminary examination of the exterior of the eye. Then, using the same instrument in a different manner, he examines the interior of the eye. With the keratometer, he measures the curvature of the outside surface of the eye, the cornea. This is the refractor, an instrument capable of duplicating nearly 1 million different lens combinations. Through the refractor, the patient's gaze is focused on a fixed point as the examiner, using a retinoscope and at the same time adjusting the refractor, determines what lens combinations will be required. He then tests the prescription by having the patient read from a chart. This is a test of far vision. In similar manner, close vision is tested. The results of all these tests may indicate the need for a clinical examination with other instruments. The slit lamp, or biomicroscope, for example, which brings the internal structure of the living eye under high magnification. The perimeter is an instrument for charting the visual field and determining blind spots in the field of vision. The binocular ophthalmoscope provides both high magnification and a depth perception for critical study of the eye's retina. From this examination and an analysis of the findings of these and other instruments, the specialist derives the lens prescription. The lens shape and the mounting for the finished lens can be selected from styles that flatter any type of face. Then, in accordance with the examiner's instructions, the ophthalmic technician selects the proper lenses, their base curves previously ground and polished at the factory. Now the other side of each lens is ground to the exact curvature specified by the prescription. And after the grinding, final polishing. Now the lens is nearly ready. In order that each one is placed in exact accordance with the prescription, optical centers and mounting angles are carefully marked. Then the edges are cut to the proper shape. Grinding the edge, the last mechanical procedure before the lens is mounted. Finally, the finished lenses are assembled in the selected spectacle frame or rimless mounting. And a last checkup, because those who work in optics are aware that no chances can be taken with human eyesight. Human eyesight, nature's most amazing achievement, corrected and improved upon through the professional skills of optical science. In every field of endeavor, greater vision, in the laboratory, higher and still higher standards of optical precision, enabling man to see further and further into the unknown. Within this little drop of water, what secret is nature withholding? What clue to the mystery of human life may be found in the microscopic study of one-time invisible subhuman life? What lies beyond tomorrow? What will be revealed to us? No one knows. No one can foretell. But one thing is certain. So long as the quest for knowledge continues, then out of the minds of technically trained, out of the crucibles, out of flame and heat, and out of the skills acquired over the years, will come new types of glass, new combinations of lenses and prisms, new instruments to perform new miracles with light, to provide the blessings and benefits of still greater vision. Toward that greater vision of the future, optical science will lead the way.